Hello, I'm Max Zukowski,
I'm Justin Osworth.
and today we're going to be discussing finite differencing.
I'm going to step out of the way and let Matt get you the introduction into the beginnings of finite differencing.
Finite differencing is a way to calculate the heat transfer by conduction and convection by modeling the flow of thermal energy within solids, static fluids, and gases. In this video, we will be focusing on solids and the boundary between solids and gases. Because a non-uniform temperature field exists within a solid, a heat flux or heat flow per unit time can be measured. For our examples today, we will be having our systems as steady state. A system is in steady state if the variables which define the behavior or process are unchanging in time. I will now start by showing a basic equation that we will be basing a lot of the material on today. This first equation is the rate of energy into the system plus the rate of energy generated by the system. And since the work done by the system is going to be equaling 0, and the mass flow rate will also be 0, this top equation can be simplified into the equation found at the bottom here. I will now be discussing the three equations that will internal energy of the system. First equation is going to be the conduction in x direction, given by this equation here, where K is going to be the thermal conductivity, A is going to be the surface area of the boundary between elements, dt is going to be the change in temperature, dx is going to be the distance in the x direction. The next equation is going to be heat transfer equation through convection, where H is going to be heat transfer coefficient, A is going to be the surface area of the boundary between elements, and dt is going to be the change in temperature. The third equation is going to be internal heat generation. Dx is going to be the change in the x direction of the element. Dy is going to be the change in the y direction of the element. Dz is going to be the change in the z direction of the element. And Q dot is going to be the volumetric heat generation.
Hey, I'm back.
And now I'm going to be discussing how to define an element.
I'll be discussing.
I'm going to be discussing how to define elements. The solid being studied is going to be divided into rectangular elements, each element containing a central node. The dimension of each element are created based on the numbers of nodes needed/wanted for analysis of the solid. More nodes mean smaller elements and greater accuracy of the solid being studied.
Now that Mac just told you what an element is, I'll be showing you how to define an element in one direction. First, you start with your part and with D, and you decide how many nodes you want to analyze. In this case, we're going to choose 5. Each node should be separated evenly across the width. So you start with 1 on each. Start with 1 on each side. Because it's 5, we're going to have 1 in the middle and 1 on each. 1, 2, 3, 4, and 5. Those are the nodes you're going to analyze. The elements are going to be split up evenly distributed in between each node, such as so here you're going to have 5 elements. You're going to get element 1, element 2, element 3, element 4, and element 5. With your elements, you might notice that here, because the node is in the middle of the element, and the node is on the edge of your piece, you have 2 half elements at 1 and 5. And the rest you have 3 full elements. The next thing you need to note is the distance between the nodes, as we will label as that will be labeled as delta x. After noticing delta x, the distance between the nodes, that will come into play when we analyze the temperature differences. The temperature difference between node 1 and 2 will be noted here, as the distance between node 1 and 2 will be noted below. before analyzing and writing down equations using our thermal conductivity, you can notice that in your part, the elements are symmetrical about the center at 3. This is important because you can get rid of half of your part because everything will be symmetrical. Whatever these temperatures come out to be will be the same on the opposite side. This is only true, however, if the boundary temperatures on each side of your part are the same. Here we've simplified it due to symmetry. On this edge, you can see the hash marks represent an insulated wall. Because the temperature on the left side and the right side of the node 3 are going to be exactly the same, we do not have to worry about any temperature change coming from that direction. We only have to worry about from this direction on node 3. On node 4, we'll have to note the temperature change from node 3 to node 5, or node 4, excuse me. And then here, you'll have to note the temperature change from node 4 to node 5. At node 5, you have to note the temperature change from node 4 to 5, and then here is our gas, air movement, and that will come into play in our convection equation over here. Next, we will draw out these equations and analyze what they mean. As noted when analyzing node 3, in the equation Q in plus Q dot equals 0, we're going to start from the left side that we have labeled over here as 0 because it's an insulated wall, so no heat will be transferred in or out from that direction. From the right side, heat will be transferred as we have our Q, our thermal conductivity, our A, our area of this element face. Then we have our temperature difference from node 4 to node 3. And that distance, delta x, separating node 3 and node 4. After that, our internal heat generation is based on the material properties, internal heat generation, and then the area of the node. In this case, it is delta x over 2 because we are only analyzing half of the node. That entire equation comes out to be, when you put them all together, comes out to be 0 for the Q in from the left, the QA times T4 minus T3 over delta x from the right, and the internal heat generation. There we go. Sorry for those technical difficulties. Next we will be analyzing node 5. On this side, you'll see from the left, we're going to have conduction, which we've noted here, the thermal conductivity by the surface area of the elements, and then the temperature change from T4 to T5 all over the distance delta x. From the right, we have convection, which we modeled from this equation. Here we have it, the H,
Heat transfer coefficient.
Heat transfer coefficient, by the area of the surface element, with the temperature change from the air, T infinity, minus the temperature of T5. The Q dot, the internal heat generation, will be the same as node 3 because it's still half an element. Delta x over 2 times Q dot. The whole equation will look like this. You have your Q in from the left, your Q in from the right, followed by your... As you can see, the board is magically different from before. But here, what we're doing is we are going to forego looking at just the equations for node 4 because you can see on both sides of the element it's going to have conduction, which we've already covered from node 3 on the right and node 5 on the left. What we have set up here are all the equations for each node, which Mac will explain a little bit.
When solving for this equation, the unknowns would be T3, T4, and T5. You have 3 equations and 3 unknowns, so you should be able to solve it.
Alright, that's all we have on finite differencing for right now. Thanks for sticking with us, and hopefully you learned a little bit of something today.
Thanks a lot for watching, and good luck on the final.